Yeah, good morning, every one of you. So, from the last class, we were seeing this humidification unit. So, in the humidification unit, so far we have seen various contents which are there in this unit, then definition of humidification and what is dehumidification and various examples. Then the basic definitions of humidity, molar humidity or mass humidity, relative humidity, factors which are affecting the relative humidity, then saturation humidity, then percentage humidity, humid heat, humid volume, then total enthalpy we have seen. And based on this, we have calculated, we have done two problems based on this one. So I hope you understood that two problems. Then we will be discussing in this class this phase equilibrium. So what is this phase equilibrium? We will be discussing. So phase equilibrium. So what is this phase equilibrium? What are the various phases which are there in this one? First, we will try to see that one. So phase equilibrium. For example, first is if there is a pool of liquid is there or water, you can consider water or liquid is there. So now in the humidification process, what is going on top of this water? Let us say some air is there. So some air is there, air or some gas is there. Okay, here what happens means, so this water has to be converted to vapor and these vapors will be getting in touch with the air or gas. Whenever they are getting in touch with air or gas, they are solubilizing inside this particular gas or air. They are getting solubilized here. So this is what happening. So first is the phase which is a gas phase is there, and or gas or vapor we can consider. Gas plus vapor will be there inside this one. And next phase is a liquid phase is there. These two phases are there. So obviously the phase equilibrium needs to be in between gas or vapor phase and liquid phase. So usually this liquid will be a single pure component. This liquid will be a single pure component. Like water is a single and it's a pure component, or something like volatile matter, acetone or something like that. It will be a single component. So in humidification or in humidification operation, the liquid phase is usually this will be a single pure component phase. Then the equilibrium partial pressure of the solute in the gas. So equilibrium partial pressure of the solute in the gas, which is nothing but solute is water vapor only, the solute. So the partial pressure of your water vapor, which is present in the gas, will be the function of a unique function of temperature. This is only the function of temperature. When the total pressure is constant, PT or capital P we are telling, this is constant when you are holding this total pressure as a constant. So the partial pressure of water vapor inside your gas phase, it will be a unique function of temperature. Also, at moderate pressures, what happens at equilibrium partial pressure? The equilibrium partial pressure will be almost independent of total pressure. So at moderate pressure values, okay, moderate pressure values, the equilibrium partial pressure means PA star is always, okay, is almost in the every case, it will be independent of temperature, independent of your total pressure, independent of total pressure. So this is valid at moderate pressures only. So at moderate pressures, the equilibrium partial pressure is almost, it is independent of the total pressure. And this equilibrium partial pressure will be usually equal to the vapor pressure of the liquid water, vapor pressure of the liquid water. In the saturation, we have already seen that. What is Hs definition? Hs is nothing but the saturation, humidity is called as a saturation humidity whenever partial pressure is equal to the vapor pressure of the liquid. Then only we are writing this formula. Vapor pressure divided by total pressure minus vapor pressure. We are writing this formula for Hs. Whereas for a humidity, normal humidity, it is a partial pressure of A divided by total pressure minus partial pressure. Like this we are writing 1 and 2. So at which the partial pressure is equal to the vapor pressure. This relationship is valid at this particular phase equilibrium conditions or the saturation conditions. So the partial pressure. So the equilibrium partial pressure is independent. Nearly it is independent of a total pressure, but it is a function of this. It is equal to the vapor pressure of the liquid phase. So vapor pressure of the liquid phase means here it will be there, vapor pressure, PA dash, vapor pressure of the liquid water. So this is a partial pressure of the solute or water vapor which is present in the gas. So by Dalton's law and also by the Raoult's law, what happens? The equilibrium partial pressure can be converted to mole fraction. So that mole fraction is denoted by YE. Therefore, this is a single component. This is a single liquid phase composition. So its equilibrium composition will be unity. Why? Because it's a single component. So here gas is there, inert gas is there, plus water vapor is also there. So two components are there. One is vapor phase, another one is a gas which is inert. So we can estimate YE, which is the equilibrium composition of your water vapor inside the gas. We can using this equation, estimate using this equation, like HS by MA divided by 1 by MB plus HS by MA. So this is called equilibrium composition of your water vapor inside your gas stream. So this relationship, this equation, this equilibrium composition is a function of temperature. It is a function of temperature. That's why we will draw, usually these values will be reported in a plot whose x-axis will be, or the abscissa, we will call x-axis as a abscissa, will be the temperature, and ordinate, which is y-axis, will be the equilibrium composition of water vapor. Then you will get like this. This relationship will be like this. Why? Because this YE, equilibrium composition, will be a function of temperature. Then the equilibrium mole fraction will be related to the saturation humidity using this equation. This is about phase equilibrium. So phase equilibrium is nothing but whenever there is a single component, single pure component is there, its equilibrium mole fraction will be equal to 1. Whenever this liquid phase is getting vaporized and it is getting solubilized into the surrounding air, its partial pressure is a unique function of temperature. Why? Because its total pressure will be held constant. Okay, because of this total pressure is constant, the partial pressure will be a function of temperature only. Then nearly at equilibrium conditions or at moderate pressure conditions, this equilibrium partial pressure is almost independent of total pressure, but it is equal to the equilibrium partial pressure is equal to the pure liquid phase vapor pressure. So vapor pressure of the pure liquid phase. Under such conditions, the function of temperature, the equilibrium mole fraction is the function of temperature. Then YE is denoted by, YE can be calculated by HS, which is saturation humidity divided by molecular weight of water vapor divided by 1 by MB. MB is the molecular weight of gas or air, then plus HS divided by MA. So this equation we can be used to calculate this YE value, mole fraction of your water vapor at equilibrium conditions in the gas phase. So this YE is a function of temperature. So we will be representing this function as a plot, equilibrium plot. So this is called as a equilibrium plot. Okay, the overall concept is called as a phase equilibrium between this vapor and gas, pure liquid and a gas phase. Is that clear?
Yes, sir.
So the next topic here, so same thing I have given here. So this phase equilibrium. So this is the phase equilibrium plot or equilibrium plot we can say. So in humidification and dehumidification operation, the liquid phase is a single pure component. Then the equilibrium partial pressure of solute in the gas phase is therefore a unique function of temperature when the total pressure on the system is held constant. Also at moderate pressures, the equilibrium partial pressure is almost independent of total pressure and it virtually equal to the vapor pressure of the liquid. By the law, Raoult's law and Dalton's law, the equilibrium partial pressure may be converted to mole fraction YE in the gas phase. Since the liquid is pure XC is always unity. Then equilibrium data are often presented as plots of YE versus T as given as PT as shown in this figure for a system of air water at 1 atm. For a system of air and water at 1 atm, so this type of equilibrium plots you will be getting. Then the equilibrium mole fraction YE is related to saturation humidity is shown in this equation. YE is equal to HS by MA divided by 1 by MB plus HS by MA. So using this Raoult's law and Dalton's law. Raoult's law is nothing but Raoult's law for the liquid phase is partial pressure is equal to vapor pressure into mole fraction, and Raoult's law for the gas phase is partial pressure is equal to total pressure into mole fraction. Then Dalton's law is sum of the partial pressures is equal to the total pressure. That is the Dalton's law using this one. So in the single slide I have given this one. You can go through phase equilibrium. Then the next topic is adiabatic saturation. So what is this adiabatic saturation? Whatever the humidification process which is going on, nothing but addition of water vapor to the surrounding gas or surrounding air is nothing but humidification process. When you are performing this humidification process under adiabatic condition, adiabatic condition means there is no heat and heat exchange between the surrounding and the system. So it is system is completely insulated. So whenever the system is completely insulated, whatever the process which is going on inside that one, it is called adiabatic process. So here the saturation process, we are saturating our surrounding air with water vapor. So in this saturation process, if it is a completely insulated chamber, under such conditions, whatever the process which is going on is called as a adiabatic saturation process. So what happens here first? So we'll try to just see what happens here in the adiabatic saturated process. So this is the topic, adiabatic saturation. Adiabatic saturation. So first of all, let us try to draw this one. Once again, the figure. So for example, there is a chamber, humidification chamber, we can call this one. So in this humidification chamber, there will be some means to let the air inside and means to let the air to flow outside of this chamber. Okay, so for example, this is like this. This chamber will be entirely insulated chamber. So this chamber will be an entirely insulated chamber. Complete insulation will be provided around the chamber. So like this. This is the insulation, insulated walls of the chamber. So you can assume this as our home cooler. Okay, cooler which will be used in our household purposes. Okay, just so these are insulated walls. So in this one, for example, air is getting inside. Okay, this is the air inlet. Okay, humidification process is nothing but transfer of your water vapor, addition of your water vapor into air, into surrounding air is called humidification process. So this humidification process only it is going on inside this one. So this is air inlet. So air will have a temperature of T, air temperature is T. Air will have a initial humidity of some H, and it will have a mole fraction of your water vapor inside this air is initially Y. Let us say that one. Then what happens inside this one, whenever air is getting inside, for example, I am taking this color for air. So air will be flowing like this. Okay, air whenever it is flowing from the inlet to the chamber. So after flowing into the chamber, so it will be occupied. Entire chamber will be occupied by the air. So why? Because there is no restriction for the air. Air will be everywhere. So inside the chamber, it will be occupied like this. Okay, then this also I am taking air only. So this color I am taking completely. It is for air. Okay, that is air inlet. Okay, air inlet. So now this is the air outlet. Okay, air outlet. So this air will come at the outlet temperature or the saturation, adiabatic saturation temperature. This is Ts, and it will have a saturation humidity Hs, and this air will have a saturation mole fraction Ys. For example, let us say this one. So these are the initial conditions before the air is getting inside, and after getting inside, it will be same as the outlet conditions. So that outlet conditions are air outlet will be the adiabatic saturation temperature Ts and adiabatic saturation humidity Hs, and saturation mole fraction of your water vapor inside your gas is Ys. So let us say this one. Then what happens inside this one? We have to add water vapor to the surrounding air. Yes. Anybody wants to say something? Okay. So we need to add water vapor to the surrounding air. So this air is before saturation. Then after entering into the chamber, what happens? There will be some spray nozzle. Sorry. There will be some spray nozzle like this. Spray nozzle will be situated. Here some nozzles will be there like this. So this nozzles, what happens? Through this nozzle, the air, the water will be sprayed like this. So spray nozzles. So this is spray nozzles. So water will be flowing like this. So whenever water is sprinkling or spraying inside the system, what happens? Some part of the water vapor will be solubilized into the surrounding air. So that is nothing but addition of water. So it is satisfying the humidification condition, because water, whenever we are spraying the water, it will be addition. Then the additional water, what happens? It will be just remain as a pool of water inside the chamber. Okay, additional water apart from the water which you are spraying. Okay, that water. So in order to facilitate the same water to be recirculation inside, there will be one pump. Okay, to recirculate inside this one, there will be pump will be there. So this pump will be recirculating this water. So some part of the water will be lost around the air. Okay, because we are adding some water vapor to the surrounding air, some part of the water will be solubilized and it will be coming outside along with the air. To replace that one, so we will be adding some makeup water. So we will be calling that as a makeup water. So inside the chamber, the temperature will be Ts only, same as the outlet temperature. Okay, adiabatic saturation temperature. In order to provide the same type of environment, same type of temperature, same temperature at the inlet condition, we have to send this makeup water at same temperature Ts condition. Okay, so this is all the humidification chamber. We will call this as an entire humidification chamber. So these are the water spray. Water spray. Whenever you spraying the water, the air is getting inlet and it is solubilizing some part of the water vapor and it is leaving outside. So in order to facilitate the recirculation of your water inside the chamber, we have to give some pump work here. Then in order to replace the liquid level inside that one, we have to give the makeup water, that too at the same temperature as the outlet temperature. That is adiabatic saturation temperature. This is the process entirely going on. During this transformation process, the air temperature is transforming from Ts to T to Ts, and humidity of the inlet air is transforming to saturation humidity, and the mole fraction of your water vapor from the inlet to outlet is changing from Y to Ys. So this is entire process is called adiabatic saturation process. So for example, this you are assuming with a cooler, okay, our home cooler. Our home cooler, what will have? So there will be a fan. Okay, this fan is nothing but a source of air. Okay, this is a source of air. So this is a chamber, our cooler chamber, this one. So backside this one, there will be some mesh type of setup will be there. Onto this one, inside there will be a pump. This pump, what it will do, whenever you are pouring some water, okay, to certain level in the cooler, so this water will be there, and this pump will just facilitate the water to be recirculated inside this one. So water will be sprinkled inside like this onto this particular mesh. Whenever you are sprinkling onto the particular mesh, whatever the air is there, which is blowing, so this is a fan, air will be blowing, no? So this, whatever the temperature which are water vapor which are sprinkling, this water vapor will be getting solubilized inside the air. So that is the addition of water. Because of this addition, whatever the temperature which is possessed by this liquid or water will be acquired by the surrounding air. then we are getting a cool breeze. Okay, cool air or cool breeze we are getting. So if the water temperature is higher temperature, okay, higher temperature, then what happens? We want the temperature of our temperature of air temperature as 30 degrees centigrades. Okay, 30 degrees centigrades. For example, outside this chamber, atmospheric temperature is, for example, it is 50 degrees centigrades. If you supply the air liquid temperature below your 30 degrees centigrades, then only you will get the overall temperature as the output breeze temperature, cool air temperature as 30 degrees centigrades. For example, if you want, if outside temperature is 50 degrees centigrades, but you want 30 degrees centigrades, but you are supplying the temperature of the liquid greater than 50 degrees centigrades or around 60 degrees centigrades. What happens? You will get more air temperature. Air temperature will be further more. So in order to have a proper cooling temperature inside the cooler, we need to supply the cool water inside that one. Then only we will get a cool breeze like that. So the same thing in the adiabatic saturator also, same thing happening in a different representation like this. Okay, I hope it is clear.
Yes, yes.
Okay. Yeah. Then in order to balance this particular chamber, there are certain assumptions are there. Okay, what are those assumptions? We will see now. So assumptions are water as well as makeup water. Okay, some part of water we are adding. Makeup water is at same temperature, that is adiabatic saturation temperature. So this is called adiabatic saturation temperature. So water as well as the makeup water, spraying water as well as makeup water, whatever we are supplying, that needs to be at the same temperature. And all the walls of the chamber are insulated. All the walls of the chamber are insulated so that we cannot exchange the heat to the outside environment. Then the latent heat of vaporization of your water vapor. So latent heat of vaporization is saturated throughout the process. Throughout the process. Why here latent heat is coming? So latent heat is coming because the liquid water is getting converted to the vapor. So there is a phase change. That's why the latent heat is coming here. So the latent heat is also at the saturated conditions according to the assumption. So to write the enthalpy balance around the tower. So to write the enthalpy balance, balance over the chamber or over the system. So pump work needs to be neglected. So we are not at all taking the energy which is required to operate the pump. So pump work we need to be neglected, and enthalpy balance is based on temperature Ts. Based on temperature Ts as datum or reference. Okay, in the total enthalpy small derivation, we have seen that one T naught will be taken as the reference or the datum line. So then this what happens? The sensible heat. So like in the total enthalpy case, what we have taken? Sensible heat of your water vapor. Water. Okay, sensible heat of your water. Then sensible heat of water, latent heat of your water vapor, latent heat of water, sensible heat of water vapor, latent heat of water, and third one is once again the sensible heat of gas. Yes, this three is the sum of your sum of the enthalpy, total enthalpy balance. Then under these conditions, there is a saturation, adiabatic condition. Entirely there is a adiabatic condition. Then what happens? Then the enthalpy of makeup water and total enthalpy of the air or gas will be equal to that of leaving gas. So where is the enthalpy addition which is coming here? So first enthalpy is from the water, the heat from the water is getting transformed to the surrounding air. So the meaning of this one is whatever the enthalpy which is given by the water or the makeup water is nothing but that is equal to the air enthalpy uh, which is coming from the air outlet. So that is the condition there. So enthalpy which is entering to the air is CS, okay, humid heat in, sorry, okay, that is, so first is makeup water supplied enthalpy, total enthalpy which is supplied inside is nothing but humid volume into T minus TS. TS here is a reference temperature. So this is nothing but a same as T naught. Earlier we have used in that formula, total enthalpy formula, plus lambda S into H is equal to lambda S into HS. So this is outlet, this is all inlet plus supplied inside the chamber using water. Okay, this is water supplied by the water. So this is inlet. Okay, then we can write this as T minus CS into T minus TS is equal to, we can take it to this side, that is lambda S into HS minus lambda S into H. Therefore, we can write CS by lambda S is equal to HS. So we can take common lambda S, lambda S. So lambda S, after taking this one more step I will write. So CS into T minus TS is equal to lambda S, you can take common, that is HS minus H. Therefore, we can write CS by lambda S is equal to HS minus H by T minus TS. By the definition of, we know that CS is nothing but humid heat. Humid heat is nothing but sum of the two quantities. One is specific heats of component B plus humidity into specific heats of component A. That we know that one. So same fact we can substitute here CS value, that is CPB plus H into CPA divided by lambda S. This is equal to CS by lambda S. So this is equal to this one, HS minus H divided by T minus TS. So here this is unknown. TS is unknown. What is this TS? Adiabatic saturation temperature is unknown here. We cannot solve this this equation directly to estimate TS value. Okay, we need some additional more conditions. Okay, to calculate that one. So HS, CS, and also lambda S. So this CS, lambda S, HS, TS, all this are all function of temperature. So they are function of temperature Ts. So Hs, comma, Cs and lambda S, they are all function of Ts. So there is an interdependency between Ts, Hs, lambda S, Cs. So because of this interdependency, we cannot directly use this equation and calculate the Ts temperature. We need to use the trial and error method. To calculate the TS value. Why? Because there is an interdependency between HS, CS and lambda S. Because of HS, CS and lambda S are the true functions of your adiabatic saturation temperature TS value. Okay, is that clear?
Yes, yes.
Okay, yeah. Please, if you have any doubts, you can ask me this one. Okay, adiabatic saturation, it's very important one. Very important. You can go through whatever the notebook has been given. So for example, this is the adiabatic saturated. So it is a technique in which a gas and liquid are brought into intimate contact for saturation to take place. So here, so this is water is the liquid and the gas is nothing but your air. So water is often sprayed into the stream of gas in a pipe or spray chamber to bring the gas to saturation. So the pipe or chamber is insulated so that the process is completely adiabatic. So water is continuously sprayed in the humidification chamber through the spray pipe or nozzle. The water at the bottom of the chamber is recirculated by a pump. So like this, it will be recirculated by using the pump. Then an air stream continuously enters into the chamber and is brought in intimate contact with the water spray. Then the air stream attains thermal equilibrium with the water and also gets saturated with water vapor at that temperature before it leaves the chamber at Ts temperature. Then the temperature at which the sensible heat gives up by the gas in cooling equals to the latent heat required to evaporate the liquid added water is called adiabatic saturation temperature. Then a small quantity of water at temperature Ts may be fed continuously to compensate for the vaporization loss of the water. This is nothing but and makeup water which will be added at only Ts temperature. Then if Y is the humidity of the inlet air and T is its temperature and lambda S is the heat of vaporization of water at the adiabatic saturation conditions. If Ts is also the reference temperature and Ys is the humidity of the saturated air leaving the chamber, then after applying the following assumptions, three assumptions, water and makeup water is at Ts and walls are insulated, then latent heat of vaporization is saturated throughout the process. So we will write the material enthalpy balance equation by taking the enthalpy of makeup water is and total enthalpy of air or gas equals to the leaving gas. So entering gas plus enthalpy which is added through the water is equal to the enthalpy of the gas which is leaving from the stream. That is Cs into T minus Ts plus lambda S into H. H is equal to lambda S into Hs. Therefore, we can write Cs divided by lambda S is equal to Hs minus H by Ts. We know that by the definition of heat, humid heat, we know that it is sum of the two heat capacities, specific heat of component B plus specific heat of component A multiplied by H. So the overall equation is this one. So we cannot directly calculate this Ts value. Why? Because this Hs, Hs, Cs and lambda S are the intimate functions of this Ts. So because of this, we need to evaluate this Ts value using the suitable trial and error method. Then only it is possible to estimate that value. Okay. So I hope it is clear to everybody. This is very important. This is very important. Please don't hesitate if you have any doubts to ask. Clear now? Shall I proceed to next topic?